Swayam Prabha. Digital India. Educated India.
Okay, so in the last class we started the method of separation of variables for the two dimensional steady state conduction in Cartesian coordinates. We tried to solve the Laplace equation. So we first proposed that product solution exists, that is t is a function of x and a function of y, which can be separated out into two solutions. That is possible only if the equation is linear, partial differential equation is linear, and you have homogeneous boundary conditions and so on. Now we got the general solution which had 4 constants. We started reducing, we started evaluating the constants one by one, and finally we came to a stage where we got the solution as an infinite series, and now with the constant En which needs to be evaluated. So I gave you a glimpse of what the En is eventually likely to be, because any function f of x can be represented as a sum of sine series or cosine series. This is what Fourier series is all about. Therefore, since there is some n pi x by L on the right side and all that, there is hope for us that we can get it in the form of we can use the series expansion and evaluate En. Once you evaluate En, then depending on the accuracy you want, you can stop your solution with E1, E2, E3, E4, up to E5, 10 terms, 15 terms. Then like a grid independent study, you will check how the solution changes to n number of terms in the expansion, and then usually 5 to 7 terms are enough. First 5 to 7 terms are enough to get a solution. Okay. Now because it involves some series expansion and it involves the property of orthogonality, we have to study about orthogonal functions. Okay. So I will call this brief 15-minute excursion as a short tour of orthogonal functions. Okay. So in a countably infinite set of functions, that is the way the mathematicians call it, solutions g1 of x gm of x and gn of x. There is basically some jargon, mathematical jargon, countably infinite set of solutions. That means you have a lot of g1, g2, g3. There is a gm and there is also gn, and it does not stop with gn, it goes beyond gn also. So in a countably infinite set of solutions, the functions are said to be termed orthogonal. In the interval a less than equal to x less than equal to b, if integral a to b gm of x into gn of x is equal to 0 for m not equal to n. We say is orthogonal, no? We will say hard work and E are orthogonal to each other means that E will not work hard. So you take these two functions, their product becomes 0 means they are orthogonal, that means they do not like each other, okay. That is why this orthogonal is also used figuratively, right. Punctuality and somebody are orthogonal to each other means he is never punctual, okay. So Gm and G are orthogonal because whenever you multiply that integral becomes 0, only under the special case when m equal to n it has a finite value, okay. Now what is a big deal about it, okay, it is orthogonal, okay, they found some function g1 g2 g are orthogonal, what is the big deal. Now if f of x is an arbitrary function of x, if f of x is an arbitrary function of x, we are exploring the possibility of representing f of x as an orthogonal, as a linear combination of orthogonal functions, okay. The idea behind defining this is basically to see whether it can be used, okay. So where is it used in mathematics, applied mathematics and engineering is to take any function f of x, a general arbitrary function of f of x, we want to see whether by using this orthogonal function g1 g2 g3 any function f of x can be represented as an infinite series, okay. So that f of x is different from g1 g2 g3, g1 g2 g3 are all certain functions which exhibit orthogonality property. If you want to make it, if you want some peace of mind now itself, I will say sin n pi x by L is an orthogonal function. All functions are not orthogonal functions, there are certain functions which are orthogonal, but our idea is to have a general function f of x, we want to represent f of x as a combination of orthogonal functions, that is I want to represent any f of x as a combination of sin pi x by L, sin 2 pi x by L, sin 3 by x by L and so on, because if I am able to do that somehow I will link it with this formula and get E of n, so that the problem gets solved. Now till I find E n my problem is not solved, okay. Let f of x be an arbitrary function, we want to explore the possibility of representing f of x as a linear combination of orthogonal function how, like this. What numbers do you want to give? Shall we go ahead with the global numbers? Shall we call this 19? Okay, so we will go ahead with the global numbers. Now let us say this f of x, let us say I want to make it as g1 of x plus c2 into g2 of x and so on up to cm gm of x and so on plus gn cn gn of x plus continuation. So what I basically want to do now is, it means f of x watch carefully, what is the logic we are trying to use? Any function f of x I want to use it as a, I want to express it as a linear combination of the orthogonal variables. Please look at this equation 20, so f of x is represented as an infinite series sigma n equal to 1 to infinity cn gn of x, it is very similar to equation 18, except that we have the same, instead of fx we have f of x minus tc, but tc is nothing but a constant. So left hand side is the same, right hand side I do not worry about En into sin n pi h by sin n pi h w by L is a constant, but g of x I do not know whether sin n pi x by is orthogonal function or not, that we have to check. Therefore equation 20 is nothing great, but from equation 20 using equation 19, if it is possible for me to extract C of n, that means I have solved this problem also. Yes, if I get Cn there, that means I will get En here. Now how do I get Cn there? Okay, what do we do for that? We have to integrate. Now if the above first of all, if the above series must be a convergent series, if it is a divergent series we have to go home, we assume that it is a convergent series. If the above series let us not get into the details of how mathematicians call it as what are the mathematical properties for making it convergent series or whatever. According to me, numerically if it is convergent, if I take the first 5 terms, if I get 0.95, if I get if I take the first 5 terms, if I get a solution as 0.8, if I take 8 terms I should get 0.82, if I get 8 terms 825. Suppose if I evaluate something, an integral, if I use 5 terms I get 100, if I do 8 terms I get 3000, if I use 10 terms I get 5000, then it is not a convergence. With increasing number of terms it should asymptotically reach some convergence, therefore there is some peace of mind for us. Okay, after 8 or 9 terms if I add more terms it will not materially alter the solution, then it is a heading towards convergence. That is E1, E1, E2, E3, E4 or C1, C2, C3, C4 will be very important compared to C11, C12, C13, C14. Later terms of the series will not contribute much to the summation. Okay, so if it is possible, if the above series is convergent and is also integrable after the multiplication, I will tell you what that multiplication is. Then integral f of n gn of x dx, I can replace the f of x by Cn, okay, Cn gn of x, I can replace the f of x by Cn gn of x. First term will be C1 g1, second term will be C2, third term C3 g3, okay. So this will be C1 nothing great. I just did f of x gn of x, for f of x I have substituted from equation 20. Okay, what is the big deal? The big deal is, there is a big deal here, the big deal is G1, G2, G3, Gn, Gm are all orthogonal functions. Therefore, all of the integrals on the right side except the Gn squared of x will all be 0 because it satisfies the orthogonality property. For any value of m not equal to n, the integral automatically becomes 0, that comes from the property of orthogonality. It is a nature of that function. Some functions satisfy that, because they are satisfying that, mathematicians have used it to our advantage to solve some equations. Okay, so this is 0, this is 0, everything is 0 except this, only one non-zero term. Exists on the right hand side. Okay. Therefore, Cn is nothing but a to b that is it. You substitute n equal to 1, you get C1, n equal to 2, C2, n equal to 3, C3, C4, you get all the Cn's. Then if you fundamentally solve the problem of expressing any f of x as an infinite series, and now by exploiting the property of the orthogonal functions you are able to get Cn, that means you have essentially solved the problem of steady state conduction in a 2-dimensional slab. It is the same f of x, Gn of x. Now one thing remains, whether sin n pi x by L is orthogonal or not, correct. If that is satisfied, then my Gn is nothing but my sin n pi x. Do not worry about this, he is a constant. Now what are these, can we give some examples of these orthogonal functions, we will see. So the short tour of orthogonal functions, okay, before it ends let us take examples of orthogonal functions. Let us take now we want to see whether it is orthogonal or not. Therefore I have to check in the interval 0 to L sin it should satisfy two things, sin n pi x by L into sin m pi x by L integral 0 till must first be 0, and when m is equal to n it should also be, it should be non-zero. If that is also 0, game close, nothing. Therefore we have to, there are two things which it has to satisfy. Now can we do this? What is sin A sin B? Cos of A minus B minus cos A plus B, huh? Okay. dx, correct. So what is integral cos n pi? Integral of cos is minus only sin, d of cos is minus sin, integral of cos is okay sin by something will come now, n minus m by all, that is okay. Let us not worry about the denominator, anyway it won't trouble. Lower limit both are 0, upper limit n is a number, m is a number, n minus m must be 0, 1, 2, 3, x by L is, am I too fast? Everything is 0, everything is 0, sin n pi x by L is orthogonal. Let us do the other one when m is equal to n, okay. So this is a big 0. So there are indeed functions represented by general g1 of x, g2 of x up to gm and gn of x, where integral a to b gm of x into gn of x equal to 0 for m not equal to n. When m equal to n, let us get rid of m, we use only n, okay. Therefore 0 to L sin squared what is sin squared theta? 1 minus cos 2 theta by 2, very good. So 1 minus whole by 2 na, whole by 2, okay, is equal to cos sin any sin of n pi, sin of 0, everything is 0. So this is nothing but L by 2, very good. What is L by 2? Half width of the slab. That integral is nothing but the half width of the slab if you translate it to our original problem. Therefore here is one sin n pi x by L which is ideally suited for us, sin n pi x into sin m pi x by L, integral 0 to L is 0. When m is equal to n, it is non-zero. Therefore it is possible for us to exploit this property of orthogonality. Fortunately for us, sin n pi x by L is already appearing here and our f of x is also here. Therefore it is possible to express f of x as an infinite series using the sin n pi x by L and comparing the left hand side and right hand side. That Cn is nothing but the En, okay. This is the way to solve this Laplace equation using the method of separation variable. So we will close this general discussion on orthogonal functions. Now we rearrange that fx minus TEC and all that. Please use whatever funda or logic I have given, please get En, substitute it into that, then we will reduce it for the special case when fx is T of hot, so that fx is a constant, then you will get the general expression. Then we look at the general expression, we look at the physical insights, whether temperature is decreasing in one direction, it is periodic in the other direction. What happens if more than one wall is at a temperature which is non-zero, and after discussing all this we will close. But before we close, Samarjit has solved this problem using a Fortran code. So for the simple case we will see how the isotherms look like, alright. So that is the program. Now please use this L by 2 business, this concept of orthogonality, and evaluate En for the problem under question. So okay. So this is like your, we don't call it f dash, no, f dash is a problem, f1 f1. So En must be f1 of x into g of x. What is g of x? No, then we cannot do this. Let us do this. So this comes here, na? Correct. So we have to keep it here. Let us keep it here, huh? Because this fellow will keep on growing. Okay, he is dependent on, okay. Now, so for this En will be equal to f of x into, take that sin h n by w also. Please evaluate. So En will be equal to f1 of x into sin n by x, correct, then into that sin h n by that is coming, where that can be taken out here, divided
by sin square n by x by l.
no, that this one must come, no, because that won't come in integration from 0 to L, okay, divided by 0 to L that sin sin h n by w by L is not coming in the denominator, huh? Is that, are you clear about that? Okay, that sin that is not coming in the denominator. Is it sin n pi in the numerator or denominator? Tell me. Why?
One more sin square xw will come. That sin will cancel out, so 1 by that will be there.
What is that sin square?
We are taking Gn equal to sin n by x by L into sin hyperbolic n by w by L. That square will come. So 1 will be cancelled out, so in the denominator only 1 will be there.
Is that clear what he is saying? Our Gn is not sin n pi x by L into sin h, because that fellow has got, unfortunately it is having n, okay. So it is multiplying the numerator, it is also multiplying, denominator is Gn square, okay, but fortunately for us it can be taken out of the integral, correct, because integration with respect to x, correct, we will cancel this. So En will be equal to denominator is what we already evaluated, L by 2, okay. Now if you go on like this it becomes very difficult. Now I will say that f of x minus tc is constant, okay, somewhere you have to make that, otherwise You have to tell what that f of x is now, right? We have come to the stage where we have to tell that. For a constant hot wall temperature of TH at the top, TC is the cold temperature at the 3 sides. Now we have now we stopped up to 20, orthogonal function. What is the equation number? 20. So this is 20, 22. So this is 23. So this is 24. Okay. Therefore, I can pull that out. Numerator integral 0 to L sin n by x by L. What is integral sin n by x by L dx? Minus so the lower limit is 1 for the numerator, correct? Cos of 0 is 1. Upper limit upper limit will keep on changing. Why? Odd and even it will change. All silver teacups. Okay. 180, 360, 720 it will alternate. Therefore, we can call this as you know that all silver teacups. So it will be something like this. Okay, cos Hn by is it okay? That L should get is that correct? I put 1 minus 1 minus minus 1 to the power of n, that is it will alternate, right? It will become 0 and this thing, right? So that 2 will come. L, is it getting cancelled? What is happening to L?
Yes sir, L is getting cancelled.
Where? Here you are getting L by 2. Is it getting cancelled or becoming L square? Tell me.
Getting cancelled.
I am not getting it. I am not able to cancel it. Where is it? The numerator divided by n pi by L. Yeah, so n pi by L gets cancelled. Okay, very good. So L gets cancelled. So what do you get? 2 Th minus Tc n pi, n pi is there. Are you sure you want to learn the method of separation of variables? 2 has taken up. Okay, all this story is to get E of n. Now substitute your E of n into the original solution, and then therefore T minus Tc is equal to I am substituting into that solution 18. Okay, this is 25 into I am not sure about that. N pi is coming, is it? Okay, into n pi, where is it going? 2 by n pi, sorry, because I was not happy with the sin h n pi y by L. Small y. Do not put sin h and w by L, that is there here. Okay, this is the way to solve it. Now let the dimensionless temperature be T minus Tc by Th minus Tc. So this dimensionless temperature phi varies between 0 and 1 in the problem, correct? We can put the 2 there.
Equal to what will connect Th minus Tc is there inside bracket.
Minus
Tc. So we are taking Th minus Tc outside.
That
is n times of that.
No, what in? No, in. That's constant. Th minus Tc is a constant everywhere in all the terms. I can pull it, no? It is something like 1, 2, 3, it is taken out, it is a constant. Okay. Now quite a formidable expression. 20 years back it is a great skill, 20, 30 years back to do all these derivations, and if you do it for a cylindrical coordinate you will get Bessel function, you will do it for a spherical coordinate you will get legendary polynomial and so on. So this is, before the advent of computers this was the only way you can attack. That is why mathematicians contributed largely to the growth of all these subjects, but now after the computer has taken over you have got MATLAB, you also got Fluent and other things where these things are numerically solved, and MATLAB you can write your script, in Fluent it is numerically solved and you can use your finite volume method to solve it. But the most important thing is the temperature is periodic about x, which you believed, 0 less than equal to x less than equal to L, so the temperature is periodic about x. This is a constant. Sin h n pi by y by L is exponential, exponentially decaying. Therefore, if the hot wall is at the top, then the temperature is exponentially decaying with y. watch carefully, the temperature is exponentially decaying with y, the temperature is periodically fluctuating with x, that means it is symmetric about x. So all the physics which was used in the formulation of the problem is intact in the solution, the physics is not at all altered, therefore the final solution should abide by the physics. So regardless of your procedure, you may use orthogonal function, Bessel function, whatever, if you get something which fundamentally violates your common sense understanding of the solution, then that solution is not correct. Okay. The other most important thing is, since n is in the denominator and with increasing n the contribution of the various terms will decrease, it will be a convergent series. N equal to 1 will have the maximum influence, the 10th term will be 1 by 10, and all these things also will have their part, okay, because sin h you can see what will happen to sin h, e to the power of mx minus e to the power of minus mx and all that, sin h by sin h, you can see all this, but since n is in the denominator, this is very clear that this will be a convergent series. Okay, the solution will be periodic about x, it will be exponential with respect to the y coordinate. Now shall we see this? Huh? This will yeah, when n tends to infinity, that means you have already added so many terms, you do not have to add that term, okay. Okay, so this gives you so please look at this graphic. So this gives a solution to the so this gives a solution. So this gives a solution to the problem, this problem for a square slab which is 10 centimeter by 10 centimeter. As you can see, so though this is a problem on steady state conduction, the K is not at all used in the problem, the thermal conductivity will enter the picture if you want to determine the heat flux at the surfaces, where it will be K dt by dx and use the Fourier's law. Temperature distribution is independent of the thermal conductivity, whereas the heat flux is, we are not worried about the heat flux here, point number 1. In here this is 10 centimeter by 10 centimeter, okay. Now this temperature, this is 100, this is 0, this is 0, this is 0, these are basically the isotherms, okay. So you can see the color code, so this is 100, this is going to be 100, this is 100, this is 100, that is why the red color is here. So this is 100, as you can see the temperature decreases. So this portion of the slab has almost reached a temperature which is between 0 and 10, we have to look at what is the value here, therefore the temperature is exponentially decaying in this direction. That means if you take this section and you plot the temperature distribution along y, it will follow the exponential decay which is picked up by this sin h n by y by L. But if you look at this section and you look at temperature on the left side and the right side at equal distance, they will be the same. Here if it is, you can see at x equal to 8 and x equal to 4, the temperature is the same, that is picked up by sin n pi x by L, okay. So the temperature, so this is a symmetric boundary condition. So this is a test we give to all our MTech students, research scholars. First exercise, solve the Laplace equation and you should get isotherms which are consistent with common sense. There is a further check, so if this is 100 0 0 0, you know that the temperature here from finite difference, you know that the temperature must be east plus north plus west plus south by 4, so the temperature at the center should be equal to 25 degrees centigrade. So as you increase the number of grids, the temperature may approach 25 either from 24.5 24.6 or it may approach from 26.2 26.1 25.8, like that it will approach. So that is another test of consistency. Now for other conditions also we have got the, so this is basically for, this is basically 3 walls at 100 and 1 wall is at 0 degree centigrade. Which wall, we will have to find out which wall is at 0 degree centigrade, can you tell us? Top wall, because the red color is here, the top wall is at 0 degree centigrade, okay. Now suppose one wall is more than one wall is at 100 degree centigrade, that means this fellow cannot handle, because it can handle only one homogeneity, because using the non-homogeneous boundary condition. See, all the boundary conditions, Dirichlet boundary conditions which were 0, we made T minus Tc and theta equal to 0 0 0 on 3 sides, we made it homogeneous, that is called homogeneous. That is, if it is a Dirichlet condition, first type of boundary condition making it 0, second type of boundary condition making dt by dx equal to 0 is called homogenization of boundary condition. Insulated boundaries are very easy to handle. In finite element we call it as natural boundary conditions. Now if you have more than one inhomogeneity, this funda of using the orthogonality and all will not work, because you can get only one constant. Then how do you solve that problem? Okay. You split using superposition. Okay, so you use what is called like that, one by one you can handle inhomogeneities on all sides. So more involved problems like this. Or you can have then you have to put minus k dt by dx equal to h delta t on the 3 walls, and then you will get some solution like lambda n tan n lambda n tan lambda nl equal to 0. So you will get transcendental equations to get the lambdas. Okay, you have to solve a transcendental equation to get the value of lambda. Now you got lambdas n pi by L because of periodic boundary condition. Even these kind of boundary conditions can be handled. Now what about this? Is correct, isn't it? There are no minus plus 2 n pi, nothing, everything is correct. So the challenge is to program it with varying number of n. Now I have solved it, compare it with what you have written in your own code. That is a good test, that is a good way of strengthening your learning. Take a problem 10 centimeter by 10 centimeter, generate phi at various values of x and various values of y, compare it with what MATLAB or Fluent or a finite difference gives. That gives a good check. Now if you have a problem like this, you can use a superposition and make it like this. Now it will just become a 100 0 0 0 problem. So you may get isotherms like this, then you cut the isotherm up to here. Okay, you just increase the geometry, take the mirror image and so at the end of the day, for this 100 0 0 problem, this is the 100 degree isotherm, it will be here only. The 0 degree isotherm is on the 3 walls. The 100 degree isotherm represents the maximum temperature in the problem, the 0 degree isotherm represents the minimum temperature in this problem. We also know that temperature is periodic about this, all the isotherms have to lie in between. Finally this is 0, so 0, 20, 30, 40, 70, 90. So when you read an isotherm, after you solve a problem and you plot it, it must be intuitively apparent that there is no violation of physics in the problem. This is the way to interpret. It should be symmetric about x, and it should the temperature must decrease exponentially from the top to the bottom. In fact, our solution confirms this, the numerical solution confirms this. Okay. So this method of separation of variables can also be used for solving the transient one dimensional conduction problem. You will use a minus lambda square, but what is the equation? 1 by alpha dou t by dou tau is dou square t by dou x square. If you use the method of separation of variables, you will get a periodic solution in x, but you will get an exponentially decaying solution in t. So if you put minus, you will get a into e to the power of minus lambda square. If you finally get the dimensional numbers, you will get Biot number, Fourier number, and you will get Biot number, Fourier number as well as x by L for that problem. But the solution, instead of having sin x and cos x, you will have for the transient conduction problem, you will still have sin n by x by L and cos n by x, no problem, but steady conduction in a cylinder you will get Bessel's function. Okay. So to recapitulate, so we use the method of separation of variables, we had a product solution, we split the solution and then we wrote the general solution, and then using by homogenizing the boundary conditions we knocked off several constants. Invoking the periodicity, we found out that there is a lambda which is n pi by L, so the solution first becomes an infinite series. Then to get the constant of the infinite series we got stuck and we exploited the property of orthogonality. Fortunately sin n pi x by L is orthogonal, and finally we got a solution, and we got a physical and intuitive feel of the solution. We also saw a numerical solution on the board, and whatever isotherms you are getting is consistent with common sense and also with our conceptual understanding of the problem. So this can be extended to transient conduction in a 1D slab, okay, where you can again use the method of separation of variables, exponential in time and periodic in x. You will get sin n pi x cos n pi x. This has been nicely worked out in the form of what is called Heisler's charts, and it is available in all books and handbooks. So either we can take the analytical solution, work out as an infinite series, or you can use Heisler's charts, or you can write your own code in MATLAB, or you can numerically solve it, or you can use a finite difference or finite volume solver like Fluent to solve this. Okay. This method of separation of variables can be applied to a select class of problems. Even for the cylinder and sphere, it will lead to Bessel function and legendary polynomial, it becomes more and more involved. These are all called classic conduction heat transfer. Okay. The other is conduction heat transfer, we can completely bypass all this and start with finite difference, finite volume, finite element, boundary element, that is applied, that is a modern approach to conduction, but this is classic. At least one or two of these elegant solutions you must know, because you are able to get a closed form solution, you can get a physical feel of the solution. When you are numerically solving, you don't know what it is giving. Okay. We will stop here.